Dear students, now we are going to a new chapter, that is compact linear map. So we know what is a linear map, the linearity of a map. Suppose x and y are any two non-linear spaces, then the linear map f from x to y, this is the linearity of f is preserved there. Then if the linear map f from x to y, which is continuous, f is continuous if and only if for any open ball u is an open ball in x, that is u equals set of all x following x with norm x less than 1. U is an open ball having a radius 1 and a center about the origin. So the linear map of f from the two non-linear spaces x to y is said to be continuous if and only for any open ball u in x, then f of u, consider this f of u is a bounded subset, which is a bounded subset of y. So this is an important definition. X and y are any two non-linear spaces, and the linear map f from x to y is continuous if there exists an open ball u, or for every open ball u in x, that is defined as in this way. For every open ball u in x, then f of u is a bounded subset of y. Okay, that is f sends an open unit ball in x to a bounded subset of y. Agree. Now, the closure. Now consider this closure of f of u. F of u is a bounded subset of y. Then the closure f of u closure is a closed bounded subset of y. F of u closure. F of u is a bounded subset of y. That is a condition for the continuity of f. Then f of u closure, the closure of f of u is a closed bounded subset of y. Then, moreover, this continuously or the linear map f from x to y is said to be compact. That's a compact linear map if the closure of f of u, that is f of u closure, is a compact subset of y, which is a compact subset of y. This f is said to be a compact linear map. F is a linear map. X and y are any two non-linear spaces. Then this the linear map f from x to y is said to be a compact map, compact linear map only when f of u closure is a compact subset of y. What about the compactness? X is a compact set, then every subset E of x is totally bounded and complete. We know what is totally bounded and what is completeness. So the linear map f from x to y is a compact linear map only when for every open ball u in x, f of u closure is a compact subset of y. So this is an important definition. What is the compactness or the compact map? A linear map where x and y are any two non-linear spaces. Then a linear map from x to y is said to be a compact linear map only when for every open ball u in x, f of u closure is a compact subset of y, and u is defined as in this way. Okay. Now we know that f of u closure is a compact subset of y. It means f of u closure is compact. F of u closure is compact means it is closed and or it is complete, not closed. It is complete and totally bounded. Complete and totally bounded. We know totally boundedness always implies boundedness, but boundedness need not be implies totally boundedness. So f of u closure is a compact subset means f of u closure is totally bounded, f of u closure is bounded, so the continuity is always preserved. So the compactness always implies continuous. If f is a compact linear map, then f is continuous. If f is a compact linear map, this implies f is a continuous map. F is continuous. Okay. So the compactness should imply continuity. Why? Because f of u closure f is a compact map only when for any open ball u in X, f of u closure is a compact subset of Y that preserves the boundedness of f of u closure. Hence, f is a continuous map. Okay. There's a question: is the continuity of f implies compactness? If the continuity implies compactness. So let us consider an example. Suppose X is an infinite dimensional normed space. X is a infinite dimensional. X is an infinite dimensional normed space. Now we define an identity map of I from X to X. I from X to X. Clearly, this I is linear and continuous. I is linear. Surely it is linear, and that's an identity function map. So surely it is continuous. Now consider suppose for any suppose U. What is U? U is an open ball, which is an open ball in X. Then clearly I of U closure. Consider this I of U closure. I of U closure is a closed unity ball. We know that f of u is an open unity ball. So u is an unity ball. Then f of u closure is a closed subset of y. Here I of u closure is closed, which is closed unity ball in X. I of u closure is a closed unity ball in X, but which is not compact. Why? Because we know that the closed and the bounded subset of X is compact only when X is of finite dimension. That's a familiar result. If the closed and bounded subset of X, suppose Y is a subset of X, which is closed subset of X, moreover Y is bounded, then this Y is compact only when X is finite dimension. X is finite dimension. Here I of u closure is a closed unity ball in X, but I of u closure need not be compact. Why? Because X is of infinite dimension. So here we see that the compactness should imply the continuity, but continuity need not be implies compactness. That is, when X and Y are any two non-linear spaces, and f from X to Y be a linear map. That's a linear map. Then f is compact. F is compact implies f is continuous. F is compact implies f is continuous. But when f is continuous, it need not be implies f is compact. Okay. So this is an important concept about this compactness and continuity. Now we are going to some propositions. First one is this theorem. Let X and Y are any two normed spaces. X and Y are any two normed spaces. F from X to Y be linear. Then f is compact. F is compact if and only if there is a necessary and sufficient argument. F is compact if and only if for every bounded sequence. for every bounded sequence xn in X, then sequence f of xn has a convergent subsequence. Has a convergent subsequence in Y. So this is an important research. X and Y are any two normed spaces. F from X to Y be linear. The linearity of F is strictly preserved there. The first part of this theorem states that when F is compact, then every bounded sequence Xn in X has a convergent subsequence. That is, proof is in this way. Come to the necessary argument. First, suppose that F is compact. F is compact. F is compact means for every open ball U is an open ball in X. U is an open ball in X. You can define this U in such a way that U equals set of all X of all in X with norm X strictly less than 1. So U is an open ball in X. And let Xn be a bounded sequence in X. Xn be a bounded sequence in X. Xn is bounded means there exists some alpha greater than 0 such that norm X strictly less than alpha. Okay. But F is compact. So by definition we know that F of U closure, since F is compact, for every open ball U in X, then F of U closure is a compact subset of Y, which is compact subset of Y. Okay, F of U closure is a compact subset of Y. Now, Xn be a bounded sequence means for some alpha is positive, norm Xn strictly less than alpha. Norm Xn strictly less than alpha means, what about norm Xn by alpha? Norm Xn by alpha less than 1. Norm Xn by alpha less than 1 means it is norm Xn by alpha in this way. Why? Because norm, it is strictly less than. Norm Xn by alpha strictly less than 1 means, what about this Xn by alpha? This Xn by alpha fall in U. But F is compact. F is compact means the continuity of F is preserved there. So Xn by alpha fall in U means F of Xn by alpha that fall in F of U. Why? Because F is compact. F is compact, that implies F is continuous. F of Xn by alpha fall in F of U. Okay. But F of U closure is a compact subset of Y. So F of U closure is a compact subset of Y means this F of Xn by alpha, which converges in F of U closure, but F of U closure is a part of. Why this is so? Because we have a familiar result. That is, when X be a matrix space, then there are some equivalent relations. One of them is, when X is compact, that's an important relation, that's an important result. X is a compact, X is a matrix space. Then X is compact, that implies every subsequence of X has a convergent subsequence. Every sequence in X has a, when X is compact, then every sequence in X has a convergent subsequence. So according to that argument, F of U closure is a compact subset of Y. So every sequence in F of U closure has a convergent sequence in Y. So F of Xn by alpha, which converges in F of U closure, which is a part of Y, that means this subsequence of F of Xn, which subsequence of F of Xn, which converges in Y. Thus, this is the necessary argument. Okay, this is because of that important, that familiar result. That is, if X is a metric space, then X is compact. Only then every sequence in X is a convergent subsequence. That is the necessary argument. What about its reverse inclusion? Come to its reverse inclusion. Reversely, let Xn be a bounded sequence in X. Xn is bounded in X. Come on, F is a linear map. F is a linear map, and f of Xn has a convergent subsequence. Has a convergent subsequence in Y. F of Xn has a convergent subsequence in Y. Then we have to show that. Then our requirement is F is compact. So in order to prove F is compact, we have to show by definition F of U closure is a compact subset of Y. This is our requirement. So for that, we can find as Xn fallen X. We can find an Xn fallen X or Xn fallen U, not Xn U. What is U? U is an open ball in X. There is, it's understood that U is an open ball in X. Then let Xn fallen U. You can find out an Xn fallen U such that norm Yn minus f of Xn strictly less than 1 by n, where n equals 1, 2, 3, etc. Where you can choose this Yn fallen f of U cross. So we have to show that our requirement is to show that f of U cross is a compact subset of U. For that, we can choose a Yn fallen f of U cross. Then we can find an element Xn in U where U is an open ball in X in such a way that norm Yn minus f of Xn strictly less than 1 by n. Why? Because of the unity. Okay, strictly less than 1 by n. Now let Xnj, sequence Xnj, be a subsequence of X. Be a subsequence of X. Xnj be a subsequence of Xn. Xnj be a subsequence of Xn. Then what is f of Xnj? F of Xnj converges to some Y fallen Y. Why? Because f of Xn has a convergent subsequence. F of Xn has a convergent subsequence in Y means this f of Xnj converges to some Y present in capital Y. Okay, right. Then the subsequence Ynj of Yn, the subsequence Ynj of Yn, which converges to Y. Okay, yes. F of Xnj converges to Y. Then Ynj be a subsequence of Yn. Surely this Ynj converges to Y. Then clearly we know that this f of U closure is compact. Why? Again, because of that theorem, if X is a metric space and X is compact, then there are some equivalent results. If X is compact, then every sequence in X is a convergent subsequence and X is complete and totally bounded. Here, every subsequence has a convergent subsequence, therefore f of U closure is complete and totally bounded, therefore f of U closure is compact. F of U closure is compact subset of Y, that means compact subset of Y, that means f of U is, or f is a compact map. Agreed.